Okay, I think I've got everything set up. Hopefully we don't have to pause or do anything like that. Okay, so today we're going to start getting into something a little bit more on the analytic side, something a little bit less concretized, something that I think is much more interesting, really, when we start getting down into it. The way that I've named this, I've just named it a general analytic approach, and that's not some codified canonical term for something. It really just means, well, here are some approaches for analysis, and let's not think too much about the semantics, and let's think about each of these concepts in turn. So the three approaches that I'm going to demonstrate, well, we've already seen a couple of these, but the three approaches that I'm going to demonstrate are a counting approach, a random sampling approach, and a closed formula approach. And all of these are in relation to some phenomenon, okay? So one of the first things we'll do is we'll define a phenomenon, and then we'll take different approaches in determining, the nature of that phenomenon, and we'll try to describe it. We'll try to analyze it in some way. So with that, let's describe kind of more generally, or more specifically, what I mean by this general analytic approach. So we're going to consider some kind of stochastic process, okay, like something with randomness in it. And remember what I said before: if we're if we're not dealing with some kind of randomness, right, in an experiment, then it might not actually be a very, very good representation of an experiment, right? An experiment has some kind of outcome that is variable. But if there's only one potential outcome, well, maybe we don't think about it like it's an experiment. Maybe we think about it a little bit differently from that. So what we're going to do is consider some kind of process, something observable, right? It could be coin flips. It could be dice rolls. It could be watching flocks of birds fly across your peripheral vision, right? Or the center of your vision, or across a camera lens. It could be fish swimming up a stream. It could be stars in the sky. It could be in photos that are taken in a very standardized way, right? Any of these could be considered some kind of stochastic process, right? You take a picture of a random place in the sky from a telescope with certain resolution of image being taken. Every one of those images is going to be different, and let's say there's going to be a different count of stars in every image, and we can start describing that. We can start thinking about it. So the way we're going to look at this is there's some kind of random process. There's some sort of phenomenon out there in the universe, and we're going to synthesize outcomes of that phenomenon, and we're going to look at the data in it, and then we're going to observe those values. We're going to try to interpret them in some way. And then we're going to see if we can answer any questions. We won't always be able to answer questions. Sometimes we'll just be descriptive, and that's completely fine. So let's start off with an idea of analysis through counting. This is what we've been doing. When we looked at permutations and combinations, factorial permutations combinations, we started off with counting, right? We started off with counting, and that's pretty powerful. Okay, so let's think about this in terms of counting in coin flips. If we're thinking about coin flips, maybe, what are the potential outcomes of a flip? A single flip is going to have either a heads or a tails, right? And we're going to assume that there's, 50-50 chance as far as those go. So let's think about 4 flips. If we're thinking about 4 flips, well, we can count out. We can count out every possible outcome, right? We can just say tails, 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 heads, tails, tails, heads, tails, and so on until we get to heads, 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 heads. So this is counting, right? In a base 2 system where the elements of the base 2 system are heads and tails. And this we can describe as being exhaustive. We're getting every possibility there, right? So we can look at a lot of phenomena through this lens. And many of those things will be within scope of the computation our computer can perform. And we can leverage our computer in that way. And that's really nice. So let's think about, I've got an example here. And where you see a lot of this come up is in the analysis of games, you could say, right? So here's a description of something you might do in a game that maybe you designed, right? So in some tabletop game that you made, when you have a battle between one character and another character, the first thing a player does is rolls a 36-sided die, then pulls a card from a standard deck of cards, and finally the player flips a coin 3 times. So how do we think about this? How can we be exhaustive about this in code? Well, it's not hard. We've already seen how to do this kind of a number of times, right? So let's break this down. If we're thinking about, well, you know what? Let me pull that slide back up since it'll be a little easier to describe this with the slide here. Okay, so in this tabletop game, the first thing you do is you roll a 36-sided die. All right, so what are the potential outcomes of a single roll of a 36-sided die? We can think about that as being the range from 1 to 36 plus 1, right? So that's easy enough to see. So 1 to 36 plus 1, right? I do that because I just want to be inclusive and communicate to the reader that, you know, I could put 37, that would be totally fine. But I like putting 36 plus 1 because I like communicating this is my intent, right? And then we're going to think about pulling a card from a standard deck of cards. Okay, well, how are we going to do that? It's actually a little bit easier than you might think. The first thing that we can do is we can define these suits, right? So we've got spades, we've got clubs, we've got diamonds, and we've got hearts. And then the next thing we can do is we can make a list of the card numbers themselves. So let's say card numbers, and this is going to be 2, 3, 4. There's a few of these, so 5, 6, 7, 8, 9, 10, Jack, Queen, King, and I'm going to just put ace last. And then I'll wrap all of these in quotes. And then the last thing that we're probably going to do, well, you know what? Let me build this deck of cards first. So let's be exhaustive with this. Like, all of our cards are going to be built with a nested for loop fairly easily. So I can just say for each suit in suits, and then for each card in the card numbers. And then from that, I can just say cards.append, and then I'll just do it like this. I'll say card of suit. And if we want to see what this looks like, that's easy. We can say for each card in cards, then we can print the card. Okay, so I'll show that in a second. And finally, the player flips a coin 3 times, right? And we already sort of touched on how to think of those coin flips. And I'll just write this code out really quick, and then we'll look at the results of that as well. So coin flips. And what I did before, let's see, we've got the potential for a flip. It's going to be heads or tails, right? Heads or tails. I'll start with tails just to make it look more like binary. And then I can say for flip 1, in flip 2 and flip 3. And then here we can say that to be exhaustive, here's our coin flips. Coin flips.append, and we can append this sublist of flip 1, flip 2, and flip 3, right? Okay, so let me go ahead and run this and just show you that we built that deck of cards, because I think that's nice to see, just to verify that that's happening the way we expect it to. And let's see. Oh, name 9 is not defined. That's because I didn't put quotes around it. And let's try that again. And notice we get this nice output, right? This is all the cards that you might get, and that's easy enough. And the I'll just comment that out, and we can look at the coin flips if we want. But you know, we know what that's going to be. It's going to be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Except tails in there for the zeros, heads in there for the ones. We're just thinking about tails as being failure and heads being success. We can think about it that way. So if we're trying to figure out the sample space for this, that's easy, right? We can just say for each roll in rolls, right? We've got rolls up here. For suit in suits, for flip in coin flips. And then we can say, well, let's append this sublist for each of these, roll, card, flip. And we can look at what this looks like. So for outcome in S, let's print each outcome and see what that looks like. So, let's see, for suit in suits, thank you, for card in suits. That makes way more sense. And, you know, what's interesting is, why did that work? That's why. Because everything's an ace. So let's run that again. That's nice. Okay. Oh, interesting. For card in card nums. Ha. Apologies, that should be card nums. I think, wait. In cards. There we go. That should do it. Right, because we should see ace of hearts and queen of hearts and things like that. Okay, and that's what we're seeing. Okay, so this is a pretty, well, why don't I just do this? I'm going to run IPython, and let's go ahead and run Analytic Approach. And, you know, we get this output, but now I can actually look at this, and I can get the length of, what is that? The length of S, right? So there's 14,976 outcomes here, right? Unique outcomes. And that's already telling us a ton about this data, right? This process in and of itself. We can see here that there are, you know, there's nearly 15,000 outcomes, and we can give a concrete response to, hey, how many different ways can you battle between these two characters? Well, this is how many ways, right? And maybe we attribute this first thing to, you know, the 36-sided die roll. Maybe we attribute that to the damage that's done, and maybe we attribute the, you know, the ace king, you know, the numeric value of the card to how much damage is absorbed, and then maybe maybe there's some modifier on that with hearts, clubs, spades, or diamonds, right? Like, okay, well, maybe in the process of getting hit, you cause some kind of collateral damage. And, you know, maybe whether or not you get hit is a matter of, well, did you get more heads than the other person, right? Like we can make this into a battle if we really want to, right? We could make player one and make player two, or, you know, make player one is like a paladin and then there's a goblin, and we can have them fight through this process. And it's not that hard, right? That's something that's accessible through, we can describe that through this counting approach. We might take a random sampling approach in order to actually make them do battle. And that's, you know, a different lens on the same phenomenon at the end of the day. So, right, the first observation we might make here is in terms of well, how many outcomes are there? That's an easy thing to do. And then we can try to answer questions. And what I'm going to do, and I'm going to, I have 5 minutes on this challenge, but I might give you a little more. I might give you like 6 or 7. I'm going to have you try to give me a response to a question related to this distribution, okay? And let me pull this up. And I'll go ahead and read through this to make sure we're on the same page. So suppose that the 36-sided die represents the range of an attack. Okay, well, cool. To hit an opponent, that opponent must be in range. For example, a roll of 29 will potentially hit another player 29 or less spaces away. The card represents the amount of damage that the attack will commit. In order to actually inflict damage, 2 of the 3 coin flips must be heads. Okay, so there's some game mechanic here. And given this game mechanic, we can answer a question: what is the probability of hitting an opponent that is 18 spaces away? Right? So you've got the code to reproduce the phenomenon, and the way to solve this is through filtering S, right? Filtering S in such a way that you get the subset A, and you can look at the magnitude or the cardinality of the subset A over the cardinality of S to answer this question. So with that, let's do 6 minutes on this, and make sure that you provide the code snippet along with the answer, right? And make sure that you round it to 3 places using the round function. So I'll go ahead and start a timer. And yeah, go for it. Okay, so I'm going to start walking through this, and I'll try to break this down into its simplest terms. So when we're looking at this, we've got this for outcome in S. I'm just going to repurpose this. We're going to need to check a couple things, right? If that outcome, if the first part of that outcome is, let's see, if it's rule of 29, okay, so 18 spaces away. We're trying to consider the probability of hitting an opponent that is 18 spaces away. And really, that should say 18 or less, shouldn't it? But, you know, here's the thing. The implication is there that it's 18 or less. So it's a little bit tricky in terms of, you know, because we're not looking for exactly 18. We're looking for 18 or less. So I'll do if the outcome, 18 or greater, right? So greater than or equal to 18. And what's the other aspect of that? It's 2 of the 3 coin flips must be heads. Okay, and outcome sub 2, right? That's the third entry in that. We need a count of heads, so that count of H has to be, well, it has to be exactly 2, it looks like from the description, right? In order to actually inflict damage, 2 of the 3 coin flips must be heads, right? So there's, you know, there's only, you know, think about that. It has to be 2 heads spaced over 3 flips. So that's interesting. Not 2 or more heads. All right, and then we can append this to, well, I'll make a collector here. Hits is going to start off like that, and we'll just say hits dot append. Let's append the outcome. And from here, we can say that the probability of this is going to be the length of the hits divided by the length of S. And I want to round that to 3 places, so I'll do that. Okay, so let's see what that gets us. Looks like it's 0.198. And I think probably, let's see, right? The tricky thing about this, the tricky thing that's in here, right, is 2 of the 3 coin flips must be heads. That's a little bit of a jerk move, you know. We could say greater than or equal to. That would be a little bit friendlier. But this is going to come up later. Like, what is the probability of getting exactly 2 out of 3 successes? And then we want to ask, well, what's the probability of getting 2 or more successes out of 3 trials, right? That's the first distribution, the first discrete distribution we're really going to look into. Cool. So let me just paste this little bit in. And remember, this is all updating on the GitHub Python file for this. Okay. All right, so let's change the story a little bit and start considering random sampling, right? So we've looked at one of our analytic approaches. That's the counting approach. Let's look at and consider a random sampling approach. So in this case, we're going to model the phenomenon using random sampling, right? And we could rewrite that prior code to be a random sampling approach, but let's look at a different problem. Let's consider invitation sent for a party, as if that happens anymore. 20 invitations are sent out. Each guest can possibly bring up to 10 guests with equal probability of between not going and 10 guests. No matter what, at least one person you will be at the party. So this is not a very straightforward phenomenon, right? It's a little bit like, well, okay, there's this sort of if-else structure built into the phenomenon itself, and we're not probably going to have some existing distribution that we can draw from. In this case, we're going to have to break this problem down a little bit. So what we're going to do is, the first step of this is we synthesize the outcomes. We model the phenomenon, except this time we're going to use randomness to draw from this. So I'm going to call choice from random. So from random, import choice. And just to remind you, what choice is going to do is it's going to pull an element with equal probability out of a list of elements, right? If I had cat, dog, ferret as a list, and I print the choice from that list, right? We're going to get one of those. There's a 1/3 probability of any one of them. Okay, so I'm going to write a function here to discover the number of attendees. So there's at least one person. That's you, the host. And then from there, we can say for whatever in range up to 20. So we're taking 20 samples here. We're going to say the number of people is going to be incremented by something in the range from 0 to 11 plus 1. Now, that's a tricky thing, right? Like, each guest can possibly bring up to 10 guests, right? So we want to be inclusive of up to 10, but we actually want to be up to and including 10. We actually want to include 11 because a person can bring 10 guests, right? There's some trickiness in there. The immediate thought is like, okay, well, it'd be, between 0 and 10 people on every sample. So we're either going to get 0 or we're going to get somewhere between 1 and 11. And that's pretty interesting. So no matter what, at least one person you will be at the party. So I think that will do it. We could make this phenomenon a little bit trickier than this, right? We could change the probabilities around the number of guests. We could say, well, maybe there's an initial binary 50-50 chance that a person will come. But I think just keeping it simple, and this is where things get a little bit arbitrary, right? You have to interpret the problem. And sometimes two different people will interpret a fairly well-stated problem in two different ways, and both those ways can be legitimate, and you can have an argument about it. And one of you tries to convince the other that it's like this, no, it's like this. Well, maybe the problem needs to be written a little bit better at some point, right? But let's go with this as what this is saying. So for each of these 20 people, we're going to get between 0 and 11 people for each of them. So if we treat this like that's the phenomenon, right? That's the phenomenon we're modeling. Then we can start interpreting the values in this phenomenon. And one of the best ways to do this, arguably the best way in kind of basic Python to do this, is to use a dictionary. And the way that we can approach some kind of closed counting of this, okay, is to sample a certain number of times. So let's imagine a party, let's imagine 100 parties that have this scenario. Let's think about all the different ways that this might go, right, in 100 samples. So if attending, so actually, let's start with attending. This is the count of people attending, right? So this is going to be the number of attendees that we're getting from this function above, right? This is just going to return an integer. It's going to be at least 1 and likely more than 1. So we're getting that number, and we're going to do this 100 times. if attending is not already in outcomes, if we don't have a recording of this count of attendees, then we're going to make an entry in those outcomes for that number of attendees. So outcomes.attending is, this is the way I do this. I initialize it to 0, and then I increment it. This is a stylistic choice. It's obviously not the only way to do this. You could make this an else statement and initialize this to 1, right? That's the equivalent statement. I think about it this way, so that's how I write code. But I don't want it to confuse anybody. It's the equivalent of having an if-else where, if you have an if-else, you would initialize that entry with 1 in that case. Okay, so let's say for, we're going to look at this dictionary now that it's populated, right? So we've taken 100 samples, and we can look at the counts of, different occurrences in these samples. So I'm going to traverse that outcomes dictionary. I'm sorting it because we're sampling, right? If we're sampling, well, the lowest number may not be the first entry in there. And dictionaries have the entry of their keys is, sort of first come, first displayed when you traverse it with a for loop. I think that's actually guaranteed now. It didn't used to be. It used to be like whatever order that ends up in. Anyway, let's look at what we might start expecting here. So this might actually be fairly difficult to interpret when you first look at it. And, but look at what the lowest number is. The lowest number of attendees is 76, and the highest number of attendees is 152. And I think this already gives you some sense of, okay, you're going to have some people at this party if this is the structure that you set up, right? Like I think it used to be in the realm of possibility, oh, no one's going to show up to this party. But obviously, I think fairly obviously, people are going to show up, right? So, what we cannot do yet is we can't answer a question like, well, how many people would you expect? And, like what we're seeing here is all these values are 1, between the highest number we're seeing is 7. And maybe that's a fluke. Maybe that's just because of this round of samples, right? If I run this again, the highest value we get is 6. Well, I think for 6 for the number of attendees at 111. But, that looks sort of like 114, doesn't it? It's close to it. And if I run this again, 110 is getting 6 people and 109 is getting 6 people. Okay, well, we might start, if we run this a number of times, we might start getting some thoughts as to how many people we could expect. Now, what I would recommend offhand is take more samples. And this is almost always the solution if you can do it. Take more samples. Let's imagine 100,000 parties instead and see what these numbers start looking like. Now, this is going to take a little while, a little longer, right? It didn't take forever, but it did take a little bit longer. And now we have some pretty standout numbers, right? And we might be able to get a better gauge of where our expectations lie. And I might put that, we don't know yet, but maybe 105 is what we might expect. Maybe that is the modal occurrence, right? The modal count of attendees at this party. Let's run this one more time and see if that still lands on 105. Now, it didn't. This time we're looking at more like 110. So maybe that was a fluke, I'm not sure. This is a fairly, this is a reasonably complex phenomenon. But what we can do, we can do a lot of things here, but one of the things we can do is we could run, if this is our set of samples, if this is our sample, right, our sample of 100,000 calls to these parties, we could run multiple trials of that sampling process and then average the results. And that's something that we're going to do later quite a bit. But here what we're seeing is, well, 108 might have the largest value. Either way, we could we could likely throw another 0 on this and be fairly more certain, right? Oh, maybe it was 112 that had the highest value. Either way, we sort of don't have enough information yet, although we could build toward having enough information. And that's nice. That is a really nice aspect of taking a sampling approach. So then we might try to answer a question. We might try to answer a question reasonably. So, given a sample of outcomes, and that sample can be just generated through one run of this, you're going to write some code to deliver the estimated probability that between 80 and 90 people will attend the party. And you're going to round that to 3 decimal places. So let's do that breakout. I'll put this up here. And let's do, well, first let me give you this code. So you're going to need to use that code, right? And I think keeping that at, well, if a million takes too long, then just move it back down to 100,000. But what you're going to do here is you're going to run this, and you're going to filter down. You're going to build your subset A, right? Sorry, you're not going to build your subset A. You're going to look at the counts for every value between 80 and 90 people, right? And then you're going to take those counts and you're going to divide them by the total. And that should give you a probability, a reasonable probability. Again, this is an estimate, and different people are going to get different answers. And what I want to see is the code that you use to do this. So I'll set a timer for, let's do 4 minutes on this. No, let's do 5. So yeah, try to get to a reasonable conclusion here. A reasonable estimate, that is. Give me a thumbs up if you'd like 2 more minutes on this. Okay, I'm going to go ahead and extend this by a couple minutes. Okay, so there are a few different ways that you could solve this. The way that I'm going to do it is just with a simple counting accumulator. So we're talking about the probability between 80 and 90 people will attend the party. And just remember, this is an estimate. It's not going to be kind of a concrete answer to this question. So we have this outcomes dictionary. And the first thing that I'm going to do is I'm going to get the total count of attendees, right? We already have that, or we should already have that. Wait, do we already have that? No, we don't. Sorry. The total is just going to be the sum of the outcomes dot values. Okay, so that's easy, right? Outcomes is dictionary, where the key is the count of. Well, let's think about this. Some of the outcome values. No, that's the number of occurrences. Doubting myself here. Let's just see. So let's do 80 and oh yeah, no, this makes sense. Okay, so 80 to 90 and this is going to start at 0, and then we'll just increment this count, right, as we see it. So for attendees in range from 80 to 90 inclusive, we can just say this 80 to 90 gets incremented, right, by by outcomes sub-attendees. Yeah, that's easy. That's an easy way to think about it. Let's do that. So the first thing will be the outcomes of the number of times 80 occurs, plus the number of times 81 occurs, plus the number of times 82 occurs. And then we're going to divide that by the total number of occurrences, which we should already know that, right? We do know that value. We have it right up here. It's 1 million. But what if we wanted to change this? Like, what if we wanted to say, make a num samples variable, right? And we could say num samples gets, how about, let's do 10,000 instead. So I think that's all we really need to do. And we're going to output this 80 to 90. Oops. Put that in a, there we go. 80 to 90. 80, 90, I think is what I called that actually. Divided by the total. And we want to round that. So why don't we do that? So round, and then I'll set that to three places. We'll print that out. And I think, barring any bugs, that should give us an answer. Okay, so, well, I'm still printing all these outcomes out. Let me just get rid of that. Okay, 0.07, all right? 0.071, 0.07, 0.077, 0.072. Okay, so we're seeing a little bit of variance in this, but that seems pretty, it seems like we're sitting right around the same values, right? So why don't we increase this number of samples to 1 million really quick and see what that looks like. And just notice here that if you increase the number of samples, you tend to gain, you tend to lower your uncertainty in a sampling process. Here what we're seeing is 0.073. I'm going to run this just one more time, and my suspicion is that we're going to see 0.073 again. Let's find out. And of course, taking more samples, 0.072. Okay, well, we're still sitting like right in there. Now, if we wanted to gain more and more surety here, maybe we could run this process with 1 million samples over a number of trials and end up with some kind of concrete result here. Let's take a break now, and when we get back, we'll look at the third strategy in an analytic approach. That's the kind of the closed formula strategy, and that's kind of the easiest one to think about. We'll just implement a formula for a known phenomenon, and then we'll analyze it. So let me just please paste my code. Sure. Let's paste from here, and then I will set a timer. For 6 minutes. All right, I'll see y'all back here in a little bit. Okay, so let's take a look at the just generally the third way that we can consider a phenomenon. And I think this one's nice in part because we're performing an approximation when we get down into this, okay? And you'll see that very shortly. But this starts off with just considering, we're considering a collection of spherical containers that we use to hold super gumballs of radius 1 inch. These containers range from 4 inches in radius up to 100 inches in radius. So consider a rough count of gumballs per sphere. All right, so where we can start with this, we've got this formula, and we can start by just writing a function that represents this formula. And we do this kind of all the time, right? We'll have some formula that we don't have built into Python, right? We'll just have to code something really quickly, and this is easy enough to do, right? From this we can say, well, from math import pi. We could hard code pi, but that's fine. And we can just make this function that we'll be using over and over again called spherical volume, and we're going to pass in a radius, and this will just simply return 4/3 times pi times radius cubed. Okay, so why don't we think about, well, what was the range here? They range from 4 inches up to 100 inches, so we could probably answer a couple quick questions. What is the smallest container size, right? That's going to be a spherical volume of 4. And what is the largest container size? Well, that should be spherical volume of 100. So let's see what that gets us. Oh, we're still performing a whole lot of computation up here somewhere. Let me stop that computation. There it is. Yep, okay. And so this is a range of volumes, and we're considering inches here. This is a range of volumes between 268 inches cubed and what is that? 4,188,790 inches cubed. So that's, we can see that range, and we can start thinking about the scales at which we're operating, right? This is, in some sense, we're synthesizing an outcome, modeling a phenomenon, and we're kind of looking at answering the basic questions about our data. But remember, these are containers to hold spherical gumballs that are all 1 inch in radius, and we probably want to start thinking about that, right? So something we might do is consider how many, very roughly, in fact, how many gumballs can we fit into one of these spherical containers. And we might take a very simple approach to that on a first pass. Now, as I write this, I want, you just think about what might be incomplete about this, because this is going to be incomplete. But remember, this is our first pass on a problem. So I'm going to call this gumball capacity, and I'm going to generate a dictionary. And in general, when we're taking this analytic approach, we're going to be packing values into a dictionary. That's going to be the thing that we do, right? Because dictionaries are a fairly complex data type that happens to be really convenient for this type of thing. It's not the best data type, but in base Python, it's kind of the best data type we have, okay? There are also NumPy arrays and pandas data frames and things like that, which you'll most likely be using primarily once you're in the DSI, and even before. So I'm going to say for every radius in range from 4 up to 100, the I'm thinking about this analysis through the lens of how many gumballs can fit in a container, right? And that's going to be easy to kind of eyeball, at least, by just saying spherical volume of R, okay? This is our spherical volume for the container, and we can divide that by the spherical volume of a gumball. And again, you know, think about what might be wrong here in this approach, okay? And if it occurs to you what might be incomplete, I don't want to say wrong, but what's incomplete, go ahead and put that into the Slack. So I'm going to go ahead and return that dictionary, and let's take a look at this. So for every radius and value, which is going to be a count of the number of gumballs, which is why I'm casting to int here. I'm throwing away the partial gumball, you could say. For every one of these in the dictionary returned from gumball capacity, we can print that radius, and we can print the value. Okay, so let's take a look at what this gives us. So our smallest container, we might claim that it can fit 64 gumballs. But if you think about this in terms of how this grows, okay, like thinking about how the volume of our containers allows the count of gumballs to grow. What does that growth look like? We can get an eye on that by looking at this, even though we're going to have some kind of inaccurate results. So what is wrong? I keep using the word wrong. I don't want to say wrong. What are we not taking into account through this expression right here? The volume of the container versus the count of gumballs that can fit in that container. What are we not taking into account? Yeah, the spaces in between the gumballs. And, we can, draw that very easily. We can say, okay, well, just if we're dealing with circles, right? We've got this space in between the circles. And if we're dealing with spheres, right, then there's even more of an issue that we're dealing with. So we might start thinking about a different approach if we want to narrow in this phenomenon, but maybe we're just trying to consider this in terms of the growth of the number of gumballs, right? And what we can say, just on a quick look of this, is that the capacity grows incredibly fast, right? And when we're looking at, this is kind of a convenient number, but when we're looking at a container with 100 that has a 100-inch radius, we arguably have space for 1 million gumballs, but as we can see, that's not actually true. But maybe it's true enough for the problem that we're going to consider here. So I'm going to have you, let me pull up this breakout because I think, I keep doing this. Let me give you the code first. So we've got this. I'll give you everything from here down. And there we go. So you're going to use that. And the question you're going to work on, I'm pulling up right now. So write a function called getSphere that takes in a number of gumballs and returns the radius of sphere necessary to accommodate that inventory. Okay? So this is answering a very different kind of question than the previous ones, but I think we can do this reasonably. And even though we're taking kind of like a very broad stroke of this, if you're given a number, well, you know what capacity what capacities can't satisfy that number, and I think that's enough of a clue to figure out, well, what is our reasonable capacity? What is the reasonable radius for a container? So you've got your code, and let's set a timer for 5 minutes. So you're going to write a function called getSphere, takes a number of gumballs, returns the radius of sphere necessary to accommodate that number of gumballs. Let me know if you want 2 more minutes on this. Okay, let's go ahead and code this function. So we take in a number of gumballs, and we return the radius of sphere necessary to accommodate that inventory. So this function, we're naming it getSphere, and we're taking in a number of gumballs. So that'll be gumballs, and I'm going to just call, this dictionary that we defined. I'm going to call gumball capacity to get that dictionary. That has all the values in it that we need. Oh, you know what? Let me move this up here. And grab that again. Okay, so I have this dictionary, and then I can say for k, v in d.items. Again, usually there's not just one way to write a function, and there's definitely another way that you could write this that would be, reasonably fine, would be totally fine as well. So if that value is greater than the gumball inventory, and this is sort of a, I don't know, it's, we're just going to look at every one of these values, and if the estimated capacity is greater than the number of gumballs, that is, then we can just return that value of k, which is the radius, right? So maybe I'll just call this radius and capacity. How about that? And if the capacity is greater than the number of gumballs, then we can return the radius. And what do we return if we don't have an appropriately sized container? Well, we could return none. That's what it returns by default. So I'm actually just going to leave that blank. So let's see what we get if we call this on. How about I do this in IPython? So I'll run that, and let's get the sphere that would accommodate, how about 567 or 5,678 gumballs. It looks like that's, it needs to have a radius of 18. What about, 40? Well, we can do that with a fairly small, we can do that with the smallest container, actually. So this is, in terms of, as far as functions go, this function has a direct business application, right? If you're in the gumball business, which I don't know how many of us are, but, we can make this better. We can make this better, actually. And we can make estimations, right, to make it better. So maybe we would think about this in terms of 1, 2, what is that? 1, 2, 3, 4. Let's say five gumballs, right? And imagining that 5 gumballs fit together, and then estimating the gap for 5 gumballs. Maybe the gap for 5 gumballs is half a gumball. And maybe we could make this original function a little bit better based on what we're seeing in the real world. Or we could just, buckle down and do some real math and, end up with a more complete formula. Maybe we'll go watch some number file videos that deal specifically with this problem and work it out from that. But really what this gives you is the ability to answer questions. And that's really what all of these approaches give us. That's what we are trying to do. We're trying to understand a phenomenon enough in order to answer a question, at least for now, right? We're going to get, y'all are going to get into more complicated spaces than that. But this is kind of the heart of this analytic approach, right? You synthesize some outcomes, in either a counting approach or in a sampling approach or in a closed formula approach. You would observe what's happening. And then you try to answer some questions as best you can. And, of course, with this get sphere, we might be wrong, right? Like we might get a good radius, but I think what's probably going to happen is we get an inventory of gumballs, and we ask, well, which sphere should we use? Which container should we use? And we actually have to set aside some small number of those gumballs because they're not going to fit in there. I think that's going to happen fairly regularly, but at least we've reasonably solved the business problem as it's stated. Okay, so let's move on to discrete distributions. And you know what? Maybe we aren't going to move into discrete quite yet. Let me just double check something. Yeah, why don't we just do that? The way that I'm going to approach this is through the lens of the first distributions that we're really going to sink into, which are the Bernoulli and binomial distributions. So why don't I just open this Bernoulli document, and we'll start with that one. Although first we're going to speak more generally on discrete random variables. There's something that we touched on before, and I'm going to bring it up again. And I'm going to bring it up again later as well. I think I bring this up 3 times total. Discrete versus continuous. How do we want to think about that? And then we're going to define a random variable. We've already done this a little bit without really realizing it. Actually, I think we explicitly did it once, but we're going to kind of codify that. And then we're going to talk about what a probability mass function is, how we think about that, what that does. And we're going to talk about the cumulative density function. When we're talking about these probabilities of specific outcomes, as we've seen in this general analytic approach, 2 of those approaches we took, we built probability mass functions, actually, by saying, well, what is the probability of this specific outcome? And we can answer questions like that. And then other kinds of questions we would be like, well, what is the probability of this range of outcomes? With the sampling approach, we didn't necessarily do that because it's not a closed formula that gives us, it's not an exact number. It's an approximation that we saw with the sampling approach that we took. So yeah, let's talk about, for the second time, let's talk about discrete versus continuous. And I like to think about this in terms of a number line. I think this is a very convenient way to represent this. When I talk about discrete, I'll often just say, okay, between 0 and 10, I usually say 9, I think. Between 0 and 9, we've got, 1, 2, 3, 4, 5, 6, 7, 8, 9. And when we describe the number 1 in this, there's nothing between 0 and 1, right? Goes 0, then 1, and then there's nothing between 1 and 2. And the application for this is very often in terms of counting, right? There are a lot of things that we count, and we don't really measure them. We don't measure the number of people. We count the number of people. It's a slight semantic difference, but you're not going to have a partial person until you start, talking about parameters like, what's the average number of people in a classroom. Then you might represent a partial person. But in general, if you're just literally counting a number of people, you're not going to say, oh, well, Jeff is only 0.3 people. That's like pretty mean to Jeff, I think, in that sense. But that's when we're thinking about a discrete concept, a discrete measurement of something, we're really thinking about there's nothing in between. We're thinking there's nothing in between 0 and 1. or there's nothing in between 2 and 3. We have discretized them. We have put strict bounds on them. And then continuous, I like to think of in terms of time. Because at this point, we don't know, well, we're not sure that time is truly continuous. It might be discretized on some level, like little tiny, time moments that are like frames in a video, like we can break video down into that. But as far as we can tell right now, physicists are, like, well, we think this is probably continuous, and we don't really know for sure. But what this means is that the precision that we can look into a value, right? If this is between 0 and 1 second, if we pick an exact moment between 0 and 1, the length of that exact moment is actually contingent on our instrument of measurement. And if we're talking theoretically, this exact moment is so exact that if we took that moment and divided it by everything else, if we were talking about, well, what's the probability of getting this exact moment in the span of a second? Well, that probability would be 0 because this actually has no dimension to it. This has no length. And so what that kind of means for us is that, well, first off, we can zoom in, right? We can say, well, what if we take this chunk of time? What if we think about this as a chunk of time instead of a discrete moment? And that chunk of time is between, 0.1 and 0.2. And then we get some other chunk of time, and we say that's between 0.11 and 0.12, and so on and so on. At some point, our instrument can't measure further than that. And that's fine. That doesn't change the continuous nature of the phenomenon. And so when we think about this, often we're thinking about continuous distributions as representing some kind of value that has decimals. And the precision of those decimals is related either to our ability to store that level of precision, right? We use 64-bit floats, which is a whole other story. But for storage of decimal numbers on our computers. And there's a point where the precision of those floats breaks in terms of the values that we give to it. But really, it's not as much about storage of the value. It's about how can we measure a precise enough value. The thing I like to talk about is you measure all the trees in a forest, then no tree, if you have the most precise, infinitely precise instrument, no two trees are going to be the same height. They can't be. And that's kind of an amazing thing to think about, that it is actually just relative to our level of precision of instrument that we're using to measure. Now, to be clear though, you can discretize continuous values, right? We do that all the time, and that's a very functional way to think about something, right? Between 0 and 1 second, let's think about this in terms of video frames. Well, we might have 29 frames in this range, right? We might have, 29 frames that sit in a video between 0 and 1 second. And we would analyze those in a discretized version of time, right? We've discretized time to 29 frames per second. We could increase that frame rate. We could decrease that frame rate. And that's a common way of thinking about things. Another way to conceptualize that in terms of discretizing things, let's think of heights of trees in a forest. And I don't know if those follow this would be a bell curve, normal distribution, however you want to think about it. We might cut this up into counts of trees that fall into certain bins, right? Although let's imagine that this is not 0. Let's imagine 0 is somewhere down here, and this is from 20 to 30 meters, and this is from 30 to 40, and this is 40 to 50, and so on, of some kind of tree. we can bin those values and say, well, let's not really worry about the difference between a tree that's 22 meters and 24 meters. Maybe we don't care about that in terms of our analysis. So we can definitely discretize continuous values, and it ends up being a lot easier to work with them if they're not in the form of continuous values. Okay. So what is a random variable? A random variable is just it's something that we use to represent the outcome of an experiment or the outcome of some some random aspect of a phenomenon. And there's always some kind of rule to this. So we might say something like let the random variable, and we might say RV, right? Let the random variable y represent heights of trees in the forest, rounded down to the nearest 10 meters. Right? And we can use this random variable y to describe the distribution. It's the characteristics of y, the distribution of y that we're really considering. And, that's just a very, that's a very simple thing to conceptualize. Okay, well, y represents the heights of trees in the forest rounded down to the nearest 10 meters. Notice there's a rule in here, the nearest 10 meters. Like we've modified the actual output of our instruments. We're not just saying, some exact value here. We've actually modified this into the description of y. So we might say something like let me make sure I don't have this as a, it's funny, the thing I was about to start talking about is actually, there's an example almost exactly like it in our notes. So let me just bring this up from our notes. So I've got something here as an example, and this is in terms of counting, which I think is really helpful. So let the random variable x represent the count of ones in a base 3 number of length 3. So the sample space of x we can see here. This is every possibility for x. This is all possible length 3 trinary outcomes. Now, this is not the sample space exactly of x because this doesn't represent the count of ones, does it? So let's think about this for a second. Let the random variable x represent the count of ones in a base 3 number of length, or a base 3 number of length 3. So we've got this count of ones. Well, let's go through these. Well, what is the count of ones here? Well, there's 0 ones in that one. There's 1 1, there's 0, 1, 2, right? 1, 0, 1, 0. And we can do that for every line. And if we do that, we can build, not only build the sample space of x, we can gain a sense of the probabilities of x equaling some specific value, right? So actually, here's our sample space of x. These are all the counts. And this is nice. It kind of has this cool symmetry to it. It's just a phenomenon, right? And, we made an arbitrary rule and we can see this sort of outcome that's kind of interesting. And then we can start asking questions and we can start answering questions as well. So what if we ask the question, what is the probability? And this is how we would do this. What is the probability that x is equal to some specific outcome, right? Some specific outcome in the sample space of x. So what is the probability that x equals 3, Now, well, how do we do that? Well, it's the same thing that we've always done. It's this, the cardinality of A over the cardinality of S. And in this case, it looks like there is only one occurrence where x is equal to 3, right? And so then we just take this whole thing, this is 3 by 9, and this looks like 1 over, 3 by 9, 27. So this is the probability that x is 3. We can answer a different kind of question, right? We can answer what is the probability x is 0, right? And then we can do the same thing. We can count the zeros. It's just 1, 2, 3, 4, 5, 6, 7, 8, 8 over 27, and that's our probability. So, this is just an indicator, it's kind of a callback to, well, we can count, right? We can count to build our sample space. But now we have this other tool where we've defined a specific variable that represents the outcome of the phenomenon. And we can take this same phenomenon and describe it in a different way, right? So let's use the same phenomenon and define a different random variable. This time we'll define a random variable y. And, we have the same space of trinary outcomes, right? This is not, these outcomes are not the sample space of y. They are the underlying phenomenon from which we can build the sample space of y. And that's really important to distinguish, right? So, y, here are our rules for this. And we're going to have a very different phenomenon as a result. Y is 0 if no 2 is present. Y is 1 if 2 is present. So if there's no 2, well, we can see this is a 0, this is a 0, this is a 1, this is a 0, this is a 0, this is a 1, this is a 1, this is a 1, this is a 1. And we could go through all of these and fill them in. And I actually have that down here. So I will pull that up. And we can see the sample space of y very clearly. This is not symmetric, right? This is a different thing that we're looking at, but the underlying phenomenon is the same phenomenon. And I think that's part of the flexibility of a random variable. We define the random variable, we put some kind of rule on it. In this case, it's a very explicitly stated rule. And what we get is something that we can calculate. So we can ask this probability question, right? Like, what is the probability that y will equal 1? And y equals 1 if 2 is present. Well, we can see the sample space of y, and all we have to do here is count the 1s and divide by 27. So again, the way that we would ask this question is, what is the probability y is equal to 1? And, something like that. And then we can just count these, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So the probability here is 19 over 27. So that's the, kind of the conceptual underpinning, right? That's the conceptual underpinning to a random variable. Now let's think about the probability mass function. And we're going to be using probability mass functions for all our discrete distributions, for the binomial distribution, for the Poisson distribution, and for the geometric distribution. And those probability mass functions are rooted in the random variable that is relative to the binomial process, or the Poisson process, or the geometric process. There are rules to that random variable that allow us to create a probability mass function. So I've got a slide here for the probability mass function, and let's talk about what this is going to do, and where it's going to do it, I guess you could say too. So what we are answering in those prior questions is something related to the probability mass function. Now, we don't know, we don't have the closed version, some mathematical representation offhand for those probability mass functions. What we're doing is just counting and dividing, but we can think about that process as yielding the result of the probability mass function. And simply what we use the PMF for is to describe the probability that a discrete random variable is equal to a specific value, right? To a specific value. Now, the way that we frame that is as we already saw it. If I've got this value x, the probability that big X is equal to some specific value. When we talk about this generically, we say the probability that big X is equal to x, to little x, right? We could put in the value 1 or 5 or 9 or whatever it might be. And usually, if you have some mathematical representation of this, we would say, like say for the Poisson distribution, the probability that x is equal to x is going to be, e to the negative lambda times lambda to the k over k factorial. You don't need to know this offhand. We're going to go over that probability mass function quite a bit. I'm just putting it here to give you a, x is equal to k in this instance. But you know what? I can just do that. I can just say k. In this case, it would be x is equal to k, but it doesn't matter, right? It's that x is going to be a specific value, right? We just describe, for Poisson, we describe that x is k, but it doesn't really matter. The probability that x is going to be specific, is going to indicate, is going to be filled with, is going to be leading to a specific value. So what is big X here? This is all possible values, right? What is k? It's a specific value. Okay. So hopefully that gives you a sense of what the probability mass function is. We're going to be working with that quite a bit. And the other thing we're going to be working with is what's called the cumulative density function. Okay, so these are the two main functions we're going to consider. The CDF, the cumulative density function, is going to be easy to represent, right? Where we say this is the probability that big X is less than or equal to some specific value, right? We could call this X, and that's fine. I'm going to call this K really quick. And if we think about this in terms of the Poisson PMF, well, we're actually going to utilize the Poisson PMF in the Poisson CDF. And we can say that this is, e to the negative lambda times, this time I'm going to say lambda to the I over I factorial. And I'm going to sum all these values from I, where I starts at 0 and goes up to k, up to and including k, okay? And what do I mean by this? Well, we're going to take the PMF of 0, of k equals 0, add that to the PMF of k equals 1, add that to the PMF of k equals 2, all the way up to the PMF of k, okay? And we're going to see this, in very clear terms in the PMFs related to each of the discrete probability distributions that we're talking about. So for those of you who haven't seen this before, or who are fairly new to this symbol, this is, we can call this capital sigma, right? It's big sigma. And this means sum. And what it does is it implies a loop, okay? The implication here is that you're going to perform some sort of loop. And if I have an example here where, I know we did this for mean, I just want to reiterate it so you're not afraid of it when you see it. If we have some list A, and A has 1, 2, 3, 4 in it, and we have this formula where we start at I. I is, in this case, I'm going to call this this position, I'm going to call this index 0. Why not? Mathematically, we often call this index 1, but let's not worry about that. Let's say that's index 0 up until, essentially the highest value of I, which is, it's going to be the number of values in A. Let's call it that. So we're going from this value up to and including that value. If I'm going to sum A sub I, then this is just going to be a for loop, right? We could call this a for loop. It's just 1 plus 2 plus 3 plus 4, right? And that's going to be 10 at the end of the day. So don't be afraid of that symbol. It just means you're going to sum whatever's to the right of it. And, that's all it means. And the CDF function, this is kind of a cool thing. Like if we think about what CDF stands for, cumulative, right? This word, cumulative density function. Cumulative implies accumulator. And very often when you have a cumulative density function, you are going to write an accumulator pattern. Not all the time, but most of the time. Most of the time you have that possibility. So let's think of an example in light of the CDF. So we usually use these, big letters, and we start with X, and then we go Y, and then Z, and then maybe C, for these different random variable names. But we often start with X. So let's let the random variable Z represent the sum of ones in 4-bit binary. So here we've got all possible 4-bit binary words: 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and so on. If we were to just count across this is just counting in binary. So we're thinking of, so these are all the possible 4-bit binary words. What are the corresponding values of Z? Well, if there are no ones, that's 0. Let me actually draw on this. So we can see that this is 0, this is 1, this is 1, this is 2, this is 1, 2, 2, 3. This is 1, 2, 2, 3, 2, 3, 3, 4. And we can take this and describe a distribution. Oh, why? Okay. All right. You know what? I forgot that it does that. There's something buggy with that thing. But what that was, this is our sample space for Z. It's 0, 1, 1, 2, 1, 2, 2, 3, 1, 2, 2, 3, 2, 3, 3, 4. Kind of a cool series in and of itself, right? Like we can see that there's a pattern there, and we could play around with that pattern. I think that would be fun. So if we want to represent Z in terms of being a distribution, we could say, well, here are all the outcomes: 0, 1, 2, 3, and 4. And then we can count these outcomes. So for 0, there's actually just one outcome that has 0 as the result. For 1, we've got 1, 2, 3, 4 outcomes, right? 1, 2, 3, 4. And for 3, we've got 1, 2, 3, 4. For 4, we have 1. And we can see that 2 has the most outcomes: 1, 2, 3, 4, 5, 6. So looking at this, what is the probability that Z is less than or equal to 2? What is that probability? And you could just represent it as a fraction. Just throw it in the Slack when you know what that is. Yeah, I see a lot of correct answers coming in. That's 11 items out of 16, and we can see that by just counting these. Okay. We've got 1 plus 4 plus 6, which is 11. So 11 sixteenths. Now, the way to, there is actually a closed CDF for this. Sorry, there's a PMF for this phenomenon. This is actually a binomial distribution. Z, in this case, follows a binomial distribution. And in this case, we have, 4 coin flips, let's say, and we're trying to find the number of successes, the probability of getting 2 or less coin flips as heads in 4 coin flips. And we can answer that pretty easily. That's actually 11 sixteenths. There are other ways to answer that with mathematical formulas. But this is an easy enough problem, so we won't worry about it here. All right, so let's, we've got 5 minutes, and I think we can touch on the first discrete distribution that we're going to talk about. Not for long, just we can just peek at it. And let me track down that slide deck. Gosh, where is it? There we go. So I want to show you where we're going with distributions, with the discrete distributions. We're going to, in our next class, we're going to talk about a few distributions. We're going to start off with the idea of a discrete probability distribution, but we already kind of understand what that is, right? If you know what a discrete random variable is, you basically know what a discrete distribution is. So we'll probably skim over that pretty quickly. Then we're going to talk about the discrete uniform distribution, how we might represent that. Then we're going to talk about what a Bernoulli trial is. I call it a Bernoulli trial. A lot of people call it Bernoulli distributions. It just, we all learn it a little differently. So I'll probably try to use those words interchangeably for Bernoulli. And then we're going to seemingly take a hard turn and really focus on counting in binary. Okay. Part of this is there's a really good algorithm to know that is the conversion from decimal to binary. We call that dec to bin. I think that's a good one to get down if you're in the habit of memorizing a couple algorithms that are kind of widely helpful. This one is interesting because there's a little bit of number theory in there, and it's also very simple. It's a simple pattern, and I think it's just a good one to learn. So we're going to take a turn and count in binary for a little bit, but then we're going to use binary for as a basis for understanding the binomial distribution. And if you notice here, the last thing we're going to do is use the PMF. I think understanding distributions through the lens of the phenomenon that creates them is really important, because you can take that and go out in the world and notice like all these other phenomena and try to synthesize the results of them, which is something we're often trying to do in data science. We're often trying to discern a function from a function space to, and we can never really find the right function, but we can find something that is good enough for our purposes. And I think understanding the underlying phenomena that create these distributions, whether it's through counting or sampling, is a better place to start than just giving you a formula that'll, give you the answer to the question, what is the probability that you get 7 heads in 14 coin flips? You could use that formula, but understanding why the probability is, some value is more important than understanding that. You can always look up a formula is kind of what I'm getting at. So that's where we're headed. And what I might do instead, since we have about 3 minutes, let's think about a uniform distribution, since we've already done so much with a uniform distribution. This random.choice function, that function acts in a way similar to what we might see when pulling a value from a discrete uniform distribution. Okay? And all we mean by uniform distribution here is that every outcome has equal probability. Okay? So you can imagine you have some hat, and you have a bunch of numbers in that hat. Let's say we've got the number 1, 3, 9, and 27. How about that? And we ask the question, what is the probability that, this random variable u for uniform, let's say, is going to equal 3? Well, we can see here that there's equal probability of any of these outcomes. And that's just going to be 1 out of 4, right? There's 4 items in there. There's equal probability of drawing any one of those. And so what does this look like when we plot it? This is going to come up a lot, and we're actually going to construct a uniform distribution using a fairly interesting approach later. If we're thinking about numbers between 0 and 10, and let's say these are discretized, right? 10? Is that 10? Oh, it doesn't matter. The probability of getting 1 is just going to be 1 out of 10, right? So the probability that, let's call this L, the probability L is going to be 1 is just going to be 1 out of 10. The probability L is 2 will also be 1 out of 10. The probability that L, and I'll leave it off on this, is less than or equal to 2 is going to be 2 out of 10, right? I think that's fairly straightforward. I think that's a really nice distribution to start with, and ends up being a construct for other distributions, and then Bernoulli will be a construct for most of the rest of our discrete distributions. So that's lecture. Thanks so much, and stay on if you have any questions. Let me stop the recording.